We are on AP Review Topic 10. This is the topic on series. And on the AP exam, there is always a series question. It is always, it seems, number 6. It's the very last FRQ. And it covers Maclaurin or Taylor series. Sometimes there will be a convergence test or something in there like that, but it's always there. This is the last unit that we covered in class, so I'm not going to spend a lot of time reviewing. We're just going to jump to these problems, and as we're going through it, I think you'll get enough of a review. All right, this first one we're doing is from 2018. Number 6, no calculator. These are always without a calculator. So it says that the Maclaurin series for natural log of 1 plus x is given by this series. So they're giving you the Maclaurin series for ln of 1 plus x. On its interval of convergence, this series converges to natural log of 1 plus x. That's what a series does. Okay? Let f be the function defined by this series. Okay? Part A, write the first 4 non-zero terms and the general term of the Maclaurin series for f. Okay? All right, well, first of all, let's look at how f relates to the given series. Okay? If I replace x with x over 3 in the series, I'll get this part of the function, and then I'll have to multiply everything by x, right? So the Maclaurin series for f will be found by multiplying x times, and I'm going to replace every x in the series with x over 3. So I have x over 3 minus, this will be, let me just write it like this, x over 3 squared over 2 plus x over 3 cubed over 3, minus x over 3 to the 4th over 4 plus ... Since we have to write the general term, I'm going to go ahead and include the general term here. So x over 3 to the n over n. Now I need to go ahead and multiply through by x. This is not a safe stop spot. We have to get it into the form of a Maclaurin series, so I need to multiply through by this x. So x squared over 3 minus, I'm going to simplify this as I do it, so this would be x squared times x, so that'll be x cubed over 3 squared times 2. See how I did that? Plus x cubed times x is x to the 4th over 3 cubed times 3 minus x to the 5th over 3 to the 4th times 4 plus ... negative 1 to the n plus 1 x to the n over 3 to the n times n. I'm sorry, x to the n plus 1. I need to multiply that by this x, so x to the n plus 1. Okay? That was worth just 2 points. 1 point was given for the first 4 terms, and 1 point was given for the general term. B. Determine the interval of convergence for the Maclaurin series for f. So determine the interval of convergence. Big points. These are always worth big points. This time it was worth 5 points. Okay? So we're going to use the ratio test. That's what we use for this. Limit, set up the ratio test. Limit as n goes to infinity, absolute value. Okay? I'm going to go to my general term. I can ignore the negative 1 because we're taking the absolute value of it, and the absolute value of negative 1 is just going to be 1. So mathematically, I don't even have to put it in here, right? So I'm going to replace n with n plus 1. So it'll be x to the n plus 2 over 3 to the n plus 1 times n plus 1. That's the n plus 1 term. And now we divide by the nth term. Since we have a fraction, I'm going to multiply by the reciprocal, which is the same thing as dividing, right? So, 3 to the n times n over x to the n plus 1. So that's the setup. That's always worth a point. And it was. 1 point was for sets up the ratio test. Okay, now we're going to, the next point is going to be awarded for computing this limit. So, but before I compute the limit, I need to simplify a little bit, see what's happening here. First, let's simplify our x terms. X to the n plus 1 divided by x to the n, x to the n plus 2 divided by x to the n plus 1. That reduces and it leaves an x on top, right? The 3's reduce. 3 to the n divided by 3 to the n plus 1 reduces and leaves a 3 on the bottom. N over n plus 1 does not reduce. It does not reduce. So I'm just going to write it there. Okay, so I've reduced what I can, and now I'm going to take this limit. Now the limit as n goes to infinity, the x over 3 is going to stay x over 3. N over n plus 1, as n goes to infinity, that goes to 1, right? The plus 1 doesn't matter. The n's reduced to 1. So that goes to 1. So this is the absolute value of x over the absolute value of 3, right? So the absolute value of x over 3. So we computed the limit, and that got us another point. Now, for this to converge, we need to make it less than 1, right? For the ratio test to converge, it's less than 1. And that means that the absolute value of x is less than 3 if we multiply both sides by 3, which means that x is between -3 and 3. Okay? Now, the ratio test does not determine convergence at these endpoints, right? Because if this limit is equal to 1, the ratio test is inconclusive. So maybe it converges, maybe it doesn't. So we have to come and test these endpoints. So let's test the endpoints at -3 first. If x is -3, then our series becomes the series of -1 to the n plus 1. I'm looking up here at this. So -1 to the n plus 1. Then we're multiplying by -3 because x is -3 to the n plus 1 divided by 3 to the n times n, right? N is going from 1 to infinity. Not that it matters. We're just looking for, does this converge or not, right? So this we can reduce as soon as I get rid of that negative. So let's get rid of that negative. This is -1 to the n plus 1 times -3 to the n plus 1 is -1 to the n plus 1 times 3 to the n plus 1. That's what -3 to the n plus 1 is. Okay? Now, -1 to the n plus 1 times -1 to the n plus 1, that is always positive. It's always positive. So that's always positive 1, right? So this is, the 3's can reduce to just 3 on the top. And we still have that n on the bottom. This is our harmonic. And a harmonic series diverges. So I'm going to put diverging harmonic series. You can also say diverging p-series. That's fine. Now so at -3 we do not include that endpoint. So that stays a less than. Now we're going to let x be positive 3. If we let x be positive 3, again, I'm going up here, I'm looking at this, and I'm putting 3 in for that x. So I'll have negative 1 to the n plus 1 times 3 to the n plus 1 divided by 3 to the n times n. Well, the 3's are going to reduce, leaving a 3 on top over that n. And now let's look at this. This is an alternating series that converges because the limit is going to 0. It's decreasing in magnitude. So this is an alternating, a converging alternating series. It converges by alternating series test. Okay, so at 3 we need to make this converge. So I'm going to say the interval of convergence is negative 3 to 3, including that positive 3. Okay, do not just go up here and put a little underline under there, okay? Because if you do, you're saying that this means that that is underlined, and it doesn't, all right? Rewrite your answer here. This was worth 5 points. 1 point for sets up ratio test. That first line, that first step. 1 point for computes the limit of the ratio. 1 point for the radius of convergence. So the radius of convergence you actually found right here or right here, okay? One of these. They both mean the same thing. So you found that here. 1 point for considers both endpoints. Considers. So even just trying to find out what these endpoints did, you considered them, right? So that even if you didn't get the correct answer here, you would have gotten that point. And then 1 point for the analysis and the interval of convergence. So 5 points, big points for finding the interval of convergence. Part C. Let P sub 4 of x be the 4th degree Taylor polynomial for f about x equals 0. Use the alternating series error bound to find an upper bound for the error. This is the error, right? Okay, so P sub 4, we don't really have to write out what P sub 4 is, but it's the first 4, it's up to the 4th degree term, okay? And if we put in 2 for, you know what, let's just write this out. P sub 4 of 2, P sub 4 of 2 would be these terms, right, where x is 2. I'd be putting 2 in for x. So that would be 2 squared over 3 minus 2 cubed over 3 squared times 2 plus 2 to the 4th over 3 cubed times 3. So I was just copying that down from up here with putting in 2 for x. That is P sub 4 of 2, right? This error will be, the actual error is everything else, right? That's everything else. But we know if the series is alternating in sign and decreasing in magnitude to 0, that the error is always less than or equal to the absolute value of this first not used term, the first unused term. So is this decreasing in magnitude to 0 and alternating in sign? Yes, it's alternating in sign. If we put 2 in for all the x's, it's alternating in sign, and it's decreasing in magnitude to 0. keeping in mind, you guys, that 2 is in our interval of convergence, right? So this does converge, so it is decreasing in magnitude to 0. So I'm going to say the Taylor series for f at x equals 2 is alternating in sign and decreasing in magnitude to 0. So that error that they tell me to write like that, so I'm going to write it how they tell me to, this error is less than or equal to the absolute value of the first unused term. Well, what is the first unused term? First unused term will be this with 2 in place of x. So 2 to the 5th, 2 to the 5th, over 3 to the 4th times 4. The absolute value of that. Okay? So the upper bound is that. So that is the upper bound. If you want to write that, you can. The upper bound is 2 to the 5th over 3 to the 4th times 4. Okay? But you don't have to write that because you said it right there. Okay, this was worth 2 points. 1 point for uses 5th degree term as error bound, and 1 point for the answer, which could be this same thing as the 5th degree term. It is the same thing. You don't have to simplify that, in other words. Okay? So that was the problem from 2018. Now let's take a look at the problem from 2016. Again, number 6. You'll see if you look through this packet, it's always number 6. No calculator. Okay? The function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It is known that f of 1 is 1, f prime of 1 is -1/2, and the nth derivative of f at x equals 1 is given by this formula. So we don't have a function for f of x, but we have all this information about it. Write the first 4 non-zero terms and the general term of the series for f about x equals 1. Remember that this is about x equals 1, right? So we're going to have a lot of x minus 1s in our Taylor series, right? So we always start by finding f of 1, but in this case they already give it to us, right? And then we go to the first derivative. The first derivative at 1 is -1/2. The second derivative at 1 is given by this formula. So the second derivative would be when n is 2. When n is 2, we're going to have a positive number, 2 minus 1 factorial over 2 to the first, like that. For the third derivative, n will be 3. -1, you know what, this was a typo. This n went outside. That was just a typo. Sorry about that. I fixed it on my new worksheets, but not on this one. But that n should be outside. -1 cubed is -1, okay? So this will be negative. And then and 3 minus 1 is 2 factorial over 2 cubed. Okay, I see what I did here. This should have been a 2 because n was 2 back then, right? This is 2 cubed. Okay? All right, so those will give me 4 non-zero terms, so I can come over here and write the Taylor series. So the Taylor series for f about x equals 1 will start with this 1, so we'll start with that 1. That's our first term. Then we go to the next term. It has this negative 1/2 in it, but that's not the only part of it, because I also have to divide by 1 factorial, which is the same thing as multiplying by 1 over 1 factorial. And then I need to multiply by x minus the center to the first power. That's my second term. Now I go to the next term. The next term will be positive 1 factorial divided by 2 squared, divided by 2 factorial, which is the same thing as multiplying our denominator by 2 factorial, times x minus 1 squared. The next term will be minus 2 factorial over 2 cubed times 3 factorial times x minus 1 cubed. And I'm going to wait until I simplify these to find the general term. Okay, so now I'm going to simplify these. Leave the 101, can't do anything with that. Minus, all right, here, this is going to reduce to 1 over 2, and I know that, but my question is, do I want to reduce it to 1 over 2, or do I want to hang on to something? So I'm going to look at my other terms to see how I want to handle this reduction. So over here I see a factorial over another factorial. I know those can be reduced. So over here, factorial over factorial, I know they're going to be able to be reduced. The denominator's factorial is always 1 larger than the numerator's, so those will reduce to just, like this would reduce just to the 3 on the bottom. This would reduce to just the 2 on the bottom. This would reduce to just the 1 on the bottom. So I'm going to write this as something over 2 times 1. Okay? Since I'm only going to be left with a 1 on top, I'm going to go ahead and move this x minus 1 to the top here. Okay? Plus, reduce. I'm going to move the x minus 1 squared on top. So I'll have 2 squared times 2. Minus, these are going to reduce. Move your x minus 1 cubed on top over 2 cubed times 3. So you could definitely leave the x's to the side, and this is not the only way you could write this, and you could definitely simplify it if you want to, but you might not see the pattern if you simplify. If you wrote this as a 2 and this as an 8 and this as a 24, you might not see the pattern there, right? So this is how I like to do it. Now comes the general term. We're alternating in signs, so I have negative 1. If I start n at 0, my first term will be positive, so that kind of makes sense to me. I'm going to do that. Okay. Now for the x's, I have all these x minus 1, so x minus 1. Their exponents differ by just 1, starting at 0, right? So this will just be n. Divided by, okay, let's go to the 2's. 2 to the first, 2 to the squared, 2 cubed, so this is 2 to the n, starting at n equals 0. And then we have 1, 2, 3, that's just n, right? Okay, now my question is, does this work for every term? Does it work for every term? And the answer is no, it does not work for every term, not if we start n at 0, because if we start n at 0, the very first term would be undefined, and it's not undefined, it's 1, right? So this is the general term for terms after the first term, right? So this is absolutely the correct answer, even though it does not work for that very first term, because I could write this as 1 plus the sum, if I start n at 1 for this next one, of that general term. Okay? So, and that's fine to do that. That's fine. So I went and looked this up on their scoring guidelines, which you can always do. on their scoring guidelines, they didn't put this, they just wrote that and they stopped, and that was their answer. Okay? So you don't have to write this here. You can just stop right there. This was worth a total of 4 points. 1 point for the first 2 terms, 1 point for the third term, 1 point for the fourth term, and 1 point for the general term. Okay. All right, I'm sure you're going to have a question about that for me, but fire away. That's all right. Part B, the Taylor series for f about x equals 1 has a radius of convergence of 2. Find the interval of convergence. Okay. Well, if we have a radius of convergence of 2 centered at 1, that means that if I did the ratio test, I would get this. I would have, we're centered at 1, right? We're centered at 1. So x would be between, we're 2 away from 1 on this side, so 3, and 2 away from 1 on this side would be a -1, right? That would yield a radius of convergence of 2 centered at x equals 1. So now I need to test the endpoints to find the interval of convergence. So at x equals -1, if we test that left endpoint, I'm going to have the sum of, and I'm looking up here at this sum, -1 to the n times -1, in place of that x will be a -2, right? -2 to the n over 2 to the n times n. So we want to see, what does this do? Well, -1 to the n, -2 to the n is -1 to the n times 2 to the n. That's what it is. Over 2 to the n. The 2 to the n's cancel, and -1 to the n times -1 to the n will always be positive. So this reduces to the sum of 1 over n, which is our diverging harmonic series, right? Now we check the other endpoint, the x equals 3, and if we put in x equals 3 to our sum, we get -1 to the n. 3 minus 1 is 2 to the n, over 2 to the n times n. The 2 to the n's cancel, and now we have our alternating harmonic series, which we know converges. This is our converging alternating harmonic, or you can say converging alternating series. So the interval of convergence is -1 to x, I'm sorry, -1 to 3, including 3, but not including -1. This was worth 2 points. 1 point for identifies the endpoints, both endpoints. And 1 point for the analysis and the interval of convergence. So 2 points. Alrighty. Part C. The Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. Okay, so f of 1.2, we're approximating that with the first 3 non-zero terms. Okay, so the first 3 non-zero terms are going to be right here. So we're going to start with 1 minus I'm putting in 1.2 for x, right? 1.2 minus 1 is just 0.2. So this is going to be 0.2 to the first over 2 times 1, or just 2, okay? Plus 0.2 squared over 2 squared times 2. And that is the approximation for f of 1.2 using the first 3 non-zero terms. Okay, did I do everything I wanted? That seemed awfully short. Did I do with all of it? I think I did. Okay? Okay. Now I want to show that the approximation, oh, that was worth just 1 point for the approximation. Okay? Show that the approximation found in part C is within 0.001 of the exact value of f of 1.2. Okay? So we're talking about error here, right? We're talking about error, and they kind of gave it away up here when they said it's an alternating series. Can we use the alternating series error bound? And yeah, we can, because when x is 0.2, we're converging. We have an alternating series that's converging then, right? So I know that this alternating series is going to be decreasing in magnitude to 0 when x is 0.2. Not when x is 4, but when x is 0.2 it is, okay? So I'm going to say that. I'm going to say that the Taylor series for f of x when x is 1.2 is alternating in sign and decreasing in magnitude to 0. So the error, I'm going to say error like this. This is how we did it in class. You could also use this minus our approximation. If I was using that, then I would name this approximation something, maybe p sub 2 of 1.2, okay, something like that. So the error here is less than or equal to the absolute value of the first omitted term. What was our first omitted term? Coming back up here, our first omitted term would be this with 1.2 in for x, right? So 1.2 in for x, that would make that 0.2 cubed over 2 cubed times 3. Extend my absolute value bars there. Okay. And now they want us to show that this is less than 0.01, right? So that's easy for me to show. It's less than 0.01. I don't need to do anything about it. If I wanted to prove it to myself, I could come down here and prove it to myself, but I'm very confident in that answer, so I'm not going to waste my time doing that. Okay, 1 point for the error form, and 1 point for the analysis. Okay. I actually did this on my, when I did it the first time, I did this, and I got this to be 1 over 3,000, okay? So it is definitely less than 1 over 1,000. Okay, let's see what's next. Next up, I'd like to do the problem from 2014 with you. Let's do this problem. Circle this. Okay. Again, number 6, of course. Okay. It says the Taylor series for a function f about x equals 1 again, about x equals 1, so we're going to have all those x minus 1s, we can't forget that, is given by this. Well, they gave it to us. That's nice. All right. We didn't have to find the Taylor series. They just gave it to us. And it converges to f of x for absolute value of x minus 1 is less than r, where r is the radius of convergence of the Taylor series. Okay. Find the value of r. Find the value of r. Well, anytime we're finding radius of convergence or interval of convergence, we're going to use the ratio test. So I'm going to set up the ratio test. Okay. So I go to my general term. I can ignore the -1 because I'm taking an absolute value, and mathematically that's going to be 1. So I don't even have to put it in there. But I need to put in everything else. So I start with the n plus 1 term, right? So we'll have 2 to the n plus 1 times x minus 1 to the n plus 1 divided by n plus 1. That's the n plus 1 term. And now we're going to multiply by the reciprocal of the nth term, because again, we're making a ratio here. Okay, so I'm going to have the n on top, the 2 to the n on the bottom, and the x minus 1 to the n on the bottom as well. So there's the setup of the ratio test. Now we need to find the limit. So I'm going to simplify this. We can simplify the 2's, and it'll leave a 2 on top, right? We can simplify the x minus 1's, and it'll leave an x minus 1 on top. The n and the n plus 1 do not reduce. We just rewrite them. Okay? Time to take the limit. Well, the limit of the 2 times the x minus 1 stays 2 times x minus 1. The limit of this, though, goes to 1 because you're left with n over n, which reduces to 1. Okay? So this limit is the absolute value of 2 times the absolute value of x minus 1. So that will be 2 times the absolute value of x minus 1. For the ratio test to converge by the ratio test, we need this to be less than 1, right? Divide both sides by the 2, and we get that. So we have found r, and r is 1/2. So it has a very small radius of convergence, just a radius of convergence of 1/2. This was worth 3 points. 1 point for sets up the ratio. Okay. 1 point for computes the limit of the ratio. And 1 point for determines the radius of convergence, r. Okay, next up, find the first 3 non-zero terms and the general term of the Taylor series for f prime, the derivative of f, about x equals 1. So I'm going to write the first few terms of just f. Okay, I'm going to write the first few terms of just f, I think. I'm going to do that first. And then I'm going to take the derivative, right? Should I do that, or should I just take the derivative of this? I don't know. What you guys would probably write out a few terms first. You know, I think I'm just going to take the derivative. So f of x is given by this series. That's f of x, right? I just copied it down exactly as they wrote it, okay? So the series for f prime of x, I'm going to take the derivative of this with respect to x, right? Taking the derivative with respect to x. So this is just a little power, and I'm going to treat n like a number, right? I'm going to treat n like a number. The negative 1 to the n plus 1 will stay because, again, it's just, I'm treating this like a number. For a derivative, for the power rule, we multiply we multiply the coefficient times n, right? Well, when I multiply the coefficient times n, the n's will reduce out, and I'll be left with just 2 to the n, and then x minus 1 to the n minus 1. We reduce that power by 1. So that's the general term for the derivative, right? They want us to write the first 3 non-zero terms. So I'm going to write the first 3 non-zero terms. We're starting n at 1, so the first power here on the negative 1 is 2, so that'll be a positive. So the first term is positive. Then we'll have 2 to the first, x minus 1 to the 0, right? Plus, now n is 2. When n is 2, we have a negative, so minus 2 to the second times x minus 1 to the first, plus, we're going to be alternating, so plus 2 to the, now we're on n is equal to 3, right? So 2 cubed, x minus 1 squared. That's the first 3 non-zero terms, right? And my general term, I already wrote the general term. So I can just do minus dot dot dot, and I'm good. Okay? This was worth 2 points for the first 3 non-zero terms, and 1 point for the general term. 3 points total. Okay, part C. The Taylor series for f prime about x equals 1 found in part B is a geometric series. Oh, okay. Find the function f prime to which the series converges for our interval of convergence, our radius of convergence, and then use this function to determine f for the interval of convergence. So let's write this series. So again, the series for f of x, I'm going to simplify this because I need to simplify this. This is going to be x minus 1 to the 0 is just 1, and so I just have 2. The first term will be 2, right? Minus, and this will be 2 squared times x minus 1 plus 2 cubed times x minus 1 squared minus dot dot dot, and then my general term there, right? Okay, so this is geometric because I am multiplying by something each time. What am I multiplying by each time to get to the next term? Well, I'm multiplying by negative 2 times x minus 1. Does that work to get to this one? Yes. I multiply by another 2, a negative 2, and another x minus 1. So this is geometric with r equals negative 2 times x minus 1. The first term, a, is 2. So if this converges, okay, so if the series converges, it must converge to a over 1 minus r, right? It must converge to that. Let's see. Find the function f prime to which the series converges. Okay, so if the series converges, f prime of x would equal this function, 2 over 1 plus 2 times x minus 1. That's what it would converge to. All right? And it converges again on the radius of convergence. The radius of convergence would only be a half. So a half unit from 1, right? Okay, now we're supposed to use this function to determine f on the radius of convergence. Okay, so this is f prime. Now we want to find f. Well, because they're making me do that, I'm going to go ahead and simplify this. Otherwise, I wouldn't simplify that. So f prime of x is equal to 2 over 1 plus 2x minus 2, right? Which is 2 over 2x minus 1. Okay? So to find f, we're going to take the integral of both sides, right? So let me scoot these closer. I'm going to take the integral of both sides. And the integral of f of x dx with respect to x. The integral of f prime of x dx is f of x plus c, but I'm going to combine the c from here with the other c over here. And this is just a little, the 2 can come out, right? Actually, we can do a little u sub here, right? If u is 2x minus 1, then du is 2 dx, which is right there. So this is exactly 1 over u du. So this is just the natural log of the absolute value of 2x minus 1. That's what it is, plus c. Okay? Now, my question is, how do we find c? We need a way to find c. Well, up here at the top, do we know what f of 0 is? Do we know what f of 1 is? 1 is our center value. So to find c, we need to know an initial condition, right? Where the series for f was centered at x equals 1. So the very first term of the series, will be f of 1, right? So f of 1, down here, f of 1 will equal the first term in the series. And the first term in the series is positive 2 over 1 times x minus 1 to the n, right? So the first term in the series, has an x minus 1 in it, right? Therefore, that has to be the first derivative term. So the f of 1 has got to be 0. It's got to be. Because if the first term here has an x in it, then there's no constant. So f of 1 must be 0. Okay? So f of 1, which is natural log of 1 plus c, must be 0. Natural log of 1 is 0, so c must be 0. So f of x must be natural log absolute value 2x minus 1. And that is true only for the interval of convergence, right? Only true on that. Same here. It's only true if that's true. Okay? All right. Tough little problem. Yeah? That was a tough one. Sometimes they throw a little zinger at you. 1 point for f prime of x, 1 point for the antiderivative, and then 1 point for f of x. Tough little problem. Wondering if you got any of it. Okay, I'll let me know. Okay, so there were our 3 examples. Now you guys go and try some on your own and let me know how you do.